Happy morning to all. I would like to welcome you all to the fifth session of the FTP on recent trends and application of NLP. I welcome the speaker of the session, Mrs. Sandhya K. Nambiar. Mrs. Sandhya K. Nambiar is the assistant professor in the
Recording in progress.
Department of Computer Science and Engineering in SEMS School of Engineering and Technology. She joined SEMS in the year of 2003. She completed her MTech degree in software engineering from Cochin University of Science and Technology in the year 2013. She is currently pursuing her PhD in the Natural Language Processing at Cochin University of Science and Technology. Her research interests include machine learning, natural language processing, and Malayalam computing.
I think the connection has
Am I
lost.
audible? Okay, I'll just introduce the speaker to you again. Mrs. Sandhya K. Nambiar. She is the assistant professor in the Department of Engineering at SEMS School of Engineering and Technology. She joined SEMS in the year 2003. Ms. Sandhya K. Nambiar has completed her MTech degree in software engineering from Cochin University of Science and Technology in 2013. She is currently pursuing her PhD in the Natural Language Processing at Cochin University of Science and Technology. Her research interests include machine learning, natural language processing, and Malayalam computing. She has published and presented many articles in journals and various international conferences. Her paper named A Bottom-Up Approach Applied to Dependency Parsing in Malayalam Language has received the Best Paper Award in 2021 IEEE 8th Uttar Pradesh Section International Conference on Electrical, Electronics and Computer Engineering. It is my esteemed pleasure to welcome Mrs. Sandhya K. Nambiar to deliver her session with us on attention mechanism on NLP.
Cynthia Miss, you are on mute.
Okay. Thank you, Ashwati. Good morning, participants. Today I am here to talk about attention mechanism in natural language processing. Introduction to attention mechanism in deep learning has improved the success of various models in recent years. Today, I'll be covering the main concept and computation behind attention mechanism. Okay, what is attention? We know that the English word attention means directing our focus at something and taking greater notice. In natural language processing, the attention mechanism is based on this concept of directing the focus, and it pays greater attention to certain factors when processing the data. Attention mechanism is a part of neural architecture that enables to dynamically highlight relevant features of the input data. It can be applied directly to the raw input or to its higher level representation. A neural network is considered to be an effort to mimic human brain actions in a simplified manner. Neural networks are computing systems with interconnected nodes that work much like neurons in the human brain. Attention mechanism is a neural network approach, is also an attempt to implement the same action of selectively concentrating on a few relevant things while ignoring others in deep neural networks. Attention is one component of a network architecture. and is in charge of managing the quantifying the interdependence. There are two types, that is interdependence between input and the output elements, and also within the input elements. Between input and output elements, we call it as general attention, and within the input elements, we call it as self-attention. Attention was originally introduced as a solution to address the main issues surrounding sequence-to-sequence model and to great success. Before going to attention model in detail, let's have a brief refreshment about sequence-to-sequence model. Sequence-to-sequence model is also known as encoder-decoder model. Actually, the main architecture behind this encoder-decoder model, the main architecture behind the sequence-to-sequence model is encoder-decoder framework. That is, in this framework, we have two components, mainly encoder component and decoder component. The encoder component, in the encoder phase, what we have to do is this encoder converts the input words to corresponding hidden vectors. That is, the word sequence should be converted to a sentence representation. Sentence representation means after passing to that layer, that encoder layer, the whole word sequence is converted to into a vector form. Okay, that vector form, for each word will get a hidden vector. Each vector represents the current word and the context of that word. And in each time step, that is for each words in the sequence, first of initial state, the first hidden state is considered as zero vector, and after passing the first word to that encoder phase, that RNN will get a hidden vector which contains the context of that first word. Okay. Then after executing the first sequence, that means first input sequence, which contains several words, right? After executing that first sequence, the final hidden vector contains all the information, all the information about all words, information about the all words in that sequence. And the decoder, after getting the final hidden state from the final word, the decoder accepts that final hidden state produced from the encoder and decodes into the probability distribution of the next possible word. So after every successive prediction, the decoder RNN uses the previous hidden state to predict the next instance of the sequence. In the picture itself, we can see that in the first picture, it is our input sequence is a French sentence. Okay. So after passing to this encoder sequence, we will get an intermediate representation. That is the vector form. Then it fed into the decoder. We will get the English sentence. Okay. And in the case of English sentence to English sentence translation, the same thing will happen. The English sentence is fed into the English encoder. We will get an intermediate representation. This intermediate representation is the universal representation. Okay. Then that final state is given to the decoder. So what happens here is the hidden vector generated in the final, that is in the encoder phase, the hidden vector, encoder hidden vector generated from the final word will contain all the information. It contains the summary of the entire input sentence. As they summarize the entire sequence in a vector form, that vector is called thought vector. Here in this figure, it represents the details of this encoder to decoder conversion. That means encoder to decoder architecture. Here, Here I'm. This is an example for machine translation that is from French to English sentence. Okay. Here in the French sentence, this input sequence contains four words: il, am, and te. This four words. First, the first word is fed into the encoder RNN. We'll get a vector representation, and this is the hidden state of the first word. Okay. Then in the second RNN, we have two inputs. That is the embedded form of the second word and also the hidden state from the previous RNN. So here we have this information about in this state, we get the information from the second word and also from the previous word. Okay. And this process continues. And in the fourth word, that is in the entire, it will get, we will get this hidden state contains hidden state contains the information from all these three words and also from the fourth word. And this fourth hidden state is the thought vector because it contains all the information. Clear? And we passes this hidden state to the decoder. And in the decoder, what we have to do is we for technical solution for technical issues, we just append two words to the start and ending position of each sequence. So in the decoder, the first word to be the first word we are going to input is the start token. After getting the start token and also from the and also the input from the encoder RNN, this will get a hidden state from the decoder RNN, and this hidden state will predict the probability of that hidden state will predict the next word, that is he. Okay. And this hidden state is transferred to the next state, and we get in the second time step what this decoder doing is the hidden state from the previous decoder RNN and also the current word. Hope this is clear. So what decoder is doing in the training phase, just as the encoder scan the input sequence word by word, similarly, the decoder will generate the output sequence word by word. Here, the input sequence we are feeding into the RNN as a word by word format, right? Similarly, as in the encoder RNN, decoder also take the input, take the that target sequence, word by word target sequence, and will generate the output sequence. Okay. The initial state of the decoder are initialized to the final state of the encoder value. Then and also the actual output, that is the expected output. In the for the expected output, the previous time step is also given as the input. So for generating heat, the previous time step is start. Okay. For generating heat, the previous time step is so what we have to do is we'll get the output from this state and also the current word he. Then it will generate the output hit. So thus we get the output he hit me with a pie. So this is the training phase of the encoder decoder.
Excuse
In
me.
the testing phase, what happens is
Excuse
encoder
me, ma'am.
plays the same role of reading the input sequence and generating the thought vectors. In the testing phase, as just like in the training phase, encoder sequence is doing same process as in the training phase. But however, in the case of decoder, now we have to predict the entire output sequence given these thought vector. So the decoder sequence predict the output sequence from these thought vector. Here, the bottleneck problem is the entire source sentence, that is, the main bottleneck problem of sequence to sequence model is the entire source sentence is represented by a single vector. So the main problem occur here is insufficient to represent all syntactic and semantic complexities, and also long-term dependency. If we are giving a long input sequence, that thought vector in a single vector format, we cannot include all the information from all words. Okay, so the solution for these two problems is, for representing syntactic and semantic complexities, we have to use a richer representation for the sentences. And in the case of long-term dependencies, take source sentence information when making next prediction. Okay, so for that, what we have to do is make relevant source sentence information available. Okay, for that, for solving this bottleneck problem, uh, we introduce the new paradigm, that is attention model. So the core idea behind the attention model is, on each step of the decoder, use direct connection to the encoder to focus on a particular part of the source sequence. So the main solution to that bottleneck problem is a mechanism by allowing the decoder to get information from all the hidden state of the encoder, not just the last hidden state. In the sequence to sequence model, we are taking the hidden state from the last word of that input sequence. Okay, and that hidden state contains the information about all the previous words also. So we are using only a single hidden state for taking as input to the decoder in the sequence to sequence model. But in the case of attention model, we are taking that thought vector, including we are taking the thought vector, and also we are taking hidden state from each RNN also. That is, from each word we'll get some one hidden state, right? So we are including both the hidden state from each word and also the thought vector. That is attention mechanism. So for doing this process, the attention mechanism requires 3 steps. That is attention score, attention distribution, and context vector. This attention score maps how well the input maps to the corresponding output. That is, look at this figure, the same encoder decoder thing. Okay, so in this case, we get a thought vector from the input sequence, that is the 4th one. Okay, and from the this thought vector is fed into the decoder state, and this decoder generate a hidden state by using that is in the decoder's first initial state. What happens is, this thought vector and the starting sequence, starting word is inputted into the decoder, will get some hidden state. Okay, some value in that hidden state, hidden vector. Okay, so what we have to do is, we take that hidden state and also from the hidden state obtained from the first word, and we compute the attention score. Attention score means we just compute the dot product between this encoder hidden state and also from the decoder hidden state. Okay, so we get a dot product value. And similarly, from the same hidden state, we have to compute the dot product of each and every hidden state from we have to compute the dot product of the hidden state produced from each and every word. Clear? So for computing the hidden state, suppose the encoder hidden state are h1, h2 up to hn. for getting the attention score of each word by is the hidden state from the decoder, dot product of hidden state from the decoder and also the hidden state from the encoder. Here I minus 1 and j represent, j is the current word, so encoder hidden state from the current word and also decoder hidden state from the previous word. Okay, so look at here. For calculating the attention score of second word. So what happens is we take the hidden state of the second word and also the decoder hidden state of the first word itself. Okay. The attention score that results from this dot product is a scalar that reflects the degree of similarity between two vectors. So we'll get a scalar value by calculating the attention score. The attention score is a scalar value. So the vector of these scores across all the encoder hidden state gives us the relevance of each encoder state to the current step of the decoder. So first what we have to do is first we have to calculate the first thing the decoder should do is they have to predict the first word. So for predicting the first word, we have to calculate the attention score of every input word. Okay, using the hidden state of those words with the hidden state of the decoder first word. Clear? Look here, we get for predicting the same first word, we have to calculate the attention score of the first word and also the second word and also the third word, and similarly we have to calculate the fourth word also. Okay, so first
Excuse me, ma'am.
yes.
Ma'am, one doubt, ma'am. Is there any to the input encoder? Is there any other hidden state passed to initial hidden state to the
Initial
input?
hidden state, I'm
In
already said about that. We are passing initial hidden state as zero vector.
Okay, that should be there with the first RNN, like encoder
Yeah,
RNN.
encoder RNN. Yes.
Okay.
Okay, clear?
Yes.
Okay. And also, we have to pass the embedded form to this encoder RNN. Okay, then we'll get a hidden value here, and we pass this hidden value to the second, then pass to the third, then pass to the fourth, and we'll get a thought vector as in the sequence to sequence model. This process is same as in the sequence to sequence model. Okay, for in the case of attention model, what we have to do is we get a thought vector here, and we'll find the hidden state of the decoder. After that, we have to calculate the attention score of every word for predicting each word in the output sequence. Clear? Okay. So thus we calculate the attention score of four words, that is il, am, entertain. So then what happens is we have to find the attention distribution. That is the second part of the attention mechanism. Say attention mechanism. In the attention mechanism, we have three steps. First one is calculating attention score. Second one is attention distribution. Then we'll get the attention output. Okay. So for calculating attention distribution, the purpose of calculating attention distribution is we'll get the output from the attention score as a scalar value. Okay, we need to normalize that value. For normalizing the attention score in between 0 to 1 range, we have to softmax each attention score. That is attention distribution. So for finding the attention distribution, take the softmax to turn the score into probability distribution. So we softmaxing all value this from the first value and also second value, third and fourth. All scores should be softmaxing. Okay, that is attention distribution. Then finally, what we have to do is we have to calculate the weighted sum of this hidden state. That is, we get the softmaxing value of these four, then we'll find the weighted sum of these values. We'll get we'll get a vector value, that is attention output, and probability of that attention output. And this attention output contains the information from the hidden state. Okay, and also it contains this information includes the high attention to the relevant word. Okay, because here we only taking the decoder hidden state of the first word. Okay, so we are using we are finding attention score of all words in the encoder with we are finding the attention score by calculating the dot product of encoder RNN with the decoder RNN, and we are taking the hidden state of decoder RNN from the first word itself. Okay, this is for predicting the first word. Clear? So the probability of the probability value gives the prediction of the first word. Similarly, so this value will get this concatenate this attention output to this hidden state, will get some y1 value, and this value predict the first word, that is he. Then what happens is we'll get the we got that first word. Then we have to predict the second word. For that purpose, we have to again calculate the attention score of each word. Clear? We have to calculate the attention word of attention score of each word of this encoder RNN by computing each hidden state to the dot product of each hidden state with the second decoder state. From this picture, you can clear that, right? Hope everyone clear?
Yes, ma'am.
Okay. So again, we have to calculate the attention score of attention score for predicting the second word. So the same process repeats. We take the second hidden state of decoder from the decoder RNN and finding the dot product with each finding the dot product with hidden state from each encoder word encoder value. Then again find the attention distribution by using softmax function. Then the weighted sum of this value will get an attention output, and this attention output sum up with this decoder hidden state again. Then we'll predict the second word hit. Similarly, in the case of third word also, again the process repeat. What happens is the third state. Here we get the decoder hidden state of the third word. How this decoder hidden state of the third word produced? Same like the sequence to sequence model. Okay, we'll get the hidden state from the previous word of the previous word from the decoder RNN, then and also from the target sequence. Then we'll calculate the decoder hidden state. Then from this, using this decoder hidden state, we compute the attention score of each word, which word is relevant, which word is mapped with this decoder hidden state. For that, we have to calculate the attention score. Okay. After calculating this attention score of each word, then again we'll calculate the attention distribution. Attention distribution is softmaxing this value. Then get the attention output by calculating the weighted sum of these values, and after that this attention output sum up with the same hidden state, same hidden value from the decoder, will get the third word. Similarly, the process repeats for every word in the output sequence. So we'll get he hit me with a pie from A, the word A will the attention mechanism predict the word pie. This pie is for is the next predicted word. Okay. After that, at last, what happens? The stop, that is end sequence. End sequence will whenever the end sequence is predicted, that is end word. We already said that we are incorporating that is we are appending two tokens start and end for each output sequence. Okay, so when the end word is predicted, that particular output predicting the output sequence will stop. Then again, will take the next input sequence. This process continues for every word in the data set. This is the training phase. Okay. Here, this figure shows the computation of the attention mechanism, much more clear. Look here. Here we have four words. This is the encoder hidden state. That is a vector generated from this encoder RNN, and this is the encoder vector generated from the second word, and this is the third word and the fourth word. Okay. Then from the decoder hidden state, what we have to do is we are for finding the score. We calculate the dot product. After that, softmaxing that score, will get a attention distribution. Okay. Then we added those attention distribution value. Okay. Then that is attention distribution. This is for the first decoder hidden state. Okay. After that, we sum up the all value and we get a context vector, and this context vector is added with this decoder hidden state. This is the decoder hidden state value, and we sum up this decoder hidden state, will get the next predicted value. Okay. So this is the basic computation behind the attention mechanism. Hope everyone clear this.
And what is the use of this multiplication?
Actually, softmaxing process is here for finding the softmaxing value. Before getting that context vector, we multiplied the score value with this hidden state. Then only we get that probability distribution. Okay.
Okay, ma'am. Thank you.
So these are the equations required for the attention mechanism. That is, let us consider the encoder hidden state as H1, H2, Hn, which we are generating from the encoder RNN. On time step, and we have decoder hidden state S1, S2 up to ST, whatever. Okay. Then we calculate the attention score ET. ET means attention score of that single decoder hidden state. That means finding the attention score of each word from using this each word in the encoder hidden state. Okay, that is ST H1. Look here, S is same. That is decoder hidden state is same, and H1 H2 is the hidden state of each encoder RNN. Okay. After that, we softmaxing the attention distribution, softmaxing this attention score for getting the attention distribution. After that, we have to calculate the weight. The same thing we have said earlier. Okay, weighted sum of the encoder hidden state. Finally, concatenating the attention output with the decoder hidden state, we get what word to be predicted. Next is, this is a basic computation behind attention mechanism. Then next is types of attention model. Two others, that is Bardino and Leon, developed two types of attention model, that is Bardino attention and Leon attention. The main difference is in the computation and order of computation. Okay. While the underlying principles of attention are same in these two types, the main difference is in the order and also in the computation. In the case of Bardino attention, look at this figure. Here what happens is encoder sequence, that is just like the sequence to sequence model. Okay. This encoder produces a hidden state for each input passed in hidden state produced at the previous time step, which is carried forward to the next step. Okay. And here in this model, additive attention is used for calculating attention score. What is doing is we are using additive attention. Okay. So it quantifies the amount of attention the decoder will place on each of the encoder output when producing the next output. So here what we have to do is we are using the additive attention. Then same as in the attention mechanism, then we softmax the alignment, that's alignment score or in the attention score to get the attention weight. Then actually what is the purpose of softmaxing? We just normalize the vector value in the range 0 to 1. Okay. Now generate the context vector by doing an element-wise multiplication. We'll get an element-wise multiplication of the attention weight with the encoder output. Then after softmaxing, we are doing that multiplication. Then only we'll get that probability distribution. Okay. Then from that, we'll get that context vector. Then what we have to do is concatenate that context vector with the previous decoder output. It is then fed into the decoder RNN cell to produce a new hidden state. Okay, based on this probability score of this hidden state, it predict the next word. Okay, so in this Bardeno attention, the process is first encoder phase, then find the attention score, then attention distribution, then attention output, then it is fed into this decoder. Okay, so we'll sum up with this decoder and we'll produce the output word. Clear? But in the case of long attention, in the long attention, the process, the attention process, that is these three steps, that is attention score, then attention weight and attention output. These three steps will be implemented after the decoding phase. That is the main difference. Okay, in the Bardeno attention, what happens is we take the encoder, we take the hidden state from the encoder, then we'll calculate alignment score or attention score, then attention distribution, then attention output, then we'll fed into this decoder. Okay, then decoder produce the final vector that which will predict the next one. But in the case of long attention, what happens is before calculating the alignment score, we fed this final hidden state, which will produce from the encoder, is fed into the decoder RNN. Okay, so in the decoder RNN, output from the previous time step to produce a new hidden state, which will be used in the subsequent step. Clear? So after completing the decoding phase, that is, we'll get a final vector from this decoding phase. What happened? We'll calculate this alignment score. So the main difference lies in the fact that decoder hidden state and the encoder hidden state are added together before being passed to the alignment score, right? First, before calculating the alignment score, we have to add the encoder hidden state as well as the decoder hidden state. This means that the decoder hidden state and encoder hidden state will not have their individual weight matrix, but we are using a shared one. We get a vector value from by adding the encoder hidden state and also the decoder hidden state. So for calculating the alignment score, here we use a tanh activation function. Will be applied on the output before being multiplied with the weight matrix. Okay, so for calculating alignment score, here we are in the Bardeno attention, we are using additive attention. Okay, for calculating the alignment score, here we are using a tanh activation function. After that, the same thing is same process is repeating. We are calculating the attention weight by finding the softmax value. Then calculate the context vector by add and sum up the weighted values, weighted vector. And in the final step, after calculating this context vector, we again concatenate this context vector with the decoder hidden state from each word. Okay, so what happens, then only we can predict the each word for the output sequence. Okay, so we have to concatenate the context vector with the decoder hidden state. So in the final step, what we have to do, context vector concatenated with the decoder hidden state. Then the probability of this combined vector will predict the next word. Hope it is clear. This is the main difference between Leong attention and Bourdieu attention. Then this mechanism improves better performance in the case of neural machine translation and also text summarization case. And this attention mechanism, the main applications of attention mechanism is machine translation, text summarization, text entailment, text simplification. For every text processing applications, we can use this attention mechanism. It is very useful to allow decoder to focus on certain part of the source. Okay, and this mechanism solve the bottleneck problem of sequence to sequence model. It allows decoder to look directly at the source and bypass that bottleneck. And the bottleneck issue, what is our bottleneck issue? We have only a single vector for collecting all the information from all words in the encoder sequence. Okay, but here in this attention mechanism, we incorporate this value, this decoder value with each and every hidden state, with the hidden state from each and every word. Okay. Attention helps with vanishing gradient problem. It provides the shortcut to faraway states and some interpretability. By inspecting attention distribution, we can see what the decoder was focusing on. Clear? In the first by using the decoder hidden state from the first word, that process is focusing on the first word, so it pays attention to that word. Okay, clear? So for getting that alignment score and the attention output, the final context vector from the attention output, it focus on that first word itself. Okay. Similarly, in the case of decoder hidden state of the second word and also in the third, etc. And this is cool. Before, we never explicitly trained an alignment system. The network just learned alignment by itself. A lot of interesting work with attention model, that is pointer network, pointer generator network modeling. Lot of works come up with this attention model. That's all. Do you have any queries? These are the references I use. That is, this first paper is Attention is All You Need. That paper is very well worth for reading this attention mechanism. And these two are the that two types of attention mechanism, Bourdieu attention and Leong attention, which was developed by Bourdieu in 2014 and Leong by 2015. Actually, this Leong attention is improvised form of Bourdieu attention, but commonly we are using this Bourdieu attention itself. Okay, that's all. Thank you. Do you have any queries? You can ask me.
Cynthia Miss, there is a question in the chat box. How can we use attention model in text summarization?
I didn't get you once more.
How can we use attention model in text summarization?
In text summarization, what we have to do is, first we have to embed the text summarization using some embedding tool, using Word2Vec or some fast text, or we can use that pre-trained BERT model. Okay. After that, that embedding value is fed into this encoder. The same mechanism we can use. The same alignment score calculation and attention weight distribution, everything we can use in this text summarization. The attention mechanism we are using in the text summarization machine for focusing the relevant words. That is same for both in any application. The one thing is we have to get a better data set, a relevant data set for the application. Any more? I hope it is clear.
Hello, any queries from the participants? You can either type in the chat box or you can unmute yourself and ask the queries.
Ma'am, what is the use of self-attention as you have explained in the first slide, self-attention?
Self-attention means that network itself network itself doing the attention part, that is focusing the relevant words. Okay, by taking the hidden state from the decoder and from the encoder and calculating this dot product and all. For each hidden state from the decoder, that network gives attention to the first word, and also and in the case of second here decoder, the network pays attention to the second word. Okay. What is the next question? How can we use attention model in text summarization? That I already said,
Yes.
right?
Next question is
How the data set will look like, what all fields are needed for Malayalam text summarization. For Malayalam text summarization, for data set we require is input sequence and also the target sequence. Input sequence, suppose there are many ways for doing this Malayalam text summarization. We can have paragraph and summary of that paragraph, or paragraph for input sequence, and also the headline. We can generate the headline for that paragraph. For the data set should require two fields, mainly the input sequence and the target sequence. And after that, we have to do some pre-processing phase, pre-processing task, then embed that this data set to a vector form. Yes, we can use this attention in Malayalam computing. We can use this attention model in Malayalam to English translation, Malayalam text summarization, Malayalam text entailment, Malayalam text simplification. In everywhere we can use this attention mechanism. Then, in the case of text summarization, in English, how can we standardize the data set we prepare for text summarization? For that question, for standardizing in the case of English text summarization, we already have some standardized data set from CNN, Daily Mail, and from some news text. Okay. But in the case of Malayalam dataset, we have to prepare. It's not yet available. We have to prepare for that. If Malayalam used, what will be in input in attention text summarization? The same thing, embedding a value, embedded value. Embedded value, that is, we get a vector form. We input this data set into the embedding tool, word embedding tool. We'll get some embedded value for each and every word. We have to input that value to this attention model. Okay, hope it's clear.
Any more? I think there is no more queries. Thank you so much, Cynthia Miss. We have got a very thorough understanding on attention mechanisms, and it was a very informative session.
I think one more question is here. Sorry, Asha.
Okay.
Is attention used in transformer model? Transformer model is the improvised form of attention model. We are using self-attention in transformer model. That is We are using, we can use attention layer, more than one attention layer in transformer model. The last session we are giving a class for transformer model. So by that time you can clear that. Okay.
So thank you,
Okay,
Cynthia
thank
Miss,
you.
for your time. So please consider this memento as a token of gratitude. Thank you so much, ma'am.
Thank you all. Thank you for
So
patiently.
for the participants, I have copied the feedback link in the chat box. Please fill that feedback link. And I request you all to join today's second session in the afternoon by 1:30 p.m. Thank you all.
Recording stopped.